Assalamualaikum warahmatullahi taala wabarakatuh and good morning. I'm Dr. Sabah Bau from the Physics Section, Pusat Pengajian Pendidikan Jarak Jauh, University Science Malaysia. This is course JIF 318, Quantum Mechanics. We are in Chapter 4 on the solutions of one-dimensional time-independent Schrödinger equation. This is Unit 4.3. In this unit, we'll discuss unbound state, that means scattering, when E is greater than V naught. That is, when the energy of the particle E is greater than the potential energy V naught. The objectives of this lesson is basically you will be able to determine the probability of scattering of a particle at a step potential here. I think this is wrong. You have to correct this. Step potential when E is greater than V naught. When the energy of the particle is greater than the potential V naught. So we'll look at the scattering from step potential when E is greater than V naught. Treat the particle as eigenfunctions of momentum that was discussed in the previous segment. Take V equal to naught for x less than 0. So here you can see that V is equal to naught. Usually we put the x-axis here, but this is to make it clearer so that you can see the step potential, where the step starts from V equal to 0 to a value V naught. Okay, and the wall of the potential is at x equal to 0. You can see here the red dash here is E. That means the energy of the particle. It is higher than V naught. That means now E is above the horizontal line representing V naught. So we have two different cases actually, either E greater than V naught or E less than V naught. So for this segment, we will consider the first one, E greater than V naught. However, before that, let us look classically in classical physics what that means. If you have this situation where E is greater than V naught, what does that mean? Classically, a particle moving to the right with E less than V naught will not be able to enter region X greater than 0. That means classically, if your E is down here, going to the right like this, the particle will be reflected back by the step potential if E is less than V naught. Okay, simply bounce back to the left with the magnitude of its velocity unchanged. Direction only changed. Initially, it moved to the right, then it hit the step potential, then it turned to the left or move to the left with the same magnitude. So if a particle with E greater than V naught, it will penetrate into the region X naught. That means if a particle moving from left to the right, but E is greater than V naught, so the particle will move unhindered. That means there is no collision with the wall, so it goes right to the right. Okay, so the particle will penetrate into region X greater than naught, but the magnitude of its velocity will decrease as its momentum decreases from P1, that is third or square root 2me to P2 square root of 2m E minus V naught, because now we have a potential of V naught there. So the momentum will decrease. So if the particle move to the right like this, initially with a momentum P1 in this region to the left of the wall here, and after passing the x equal to 0, this is P2. The momentum changes because of the difference in the E and V naught. But it will go right to the right without any of the particle will be reflected back or being scattered by the wall. That's in classical physics. Okay. So in quantum mechanics, let us check case 1, E greater than V naught. Quantum mechanics predicts a very different behavior. Remember that if in classical physics, if E is less than V naught, the particle will be reflected back. If you have 10 particles, 10 particles will be reflected back. If you have particle with energy E greater than V naught, all particles will pass through. That means it can go to the right without any being reflected back, except that the momentum changes. The momentum of the particle changes. But in quantum mechanics, it predicts a very different behavior. Let us check on it. Schrodinger equation for a constant potential has the form, is the same form in the previous segment. That means in the form of energy. For x less than 0, that means when v equal to 0. Here when v equal to 0. Look back at the diagram. Okay. And with E in minus V not for x greater than, that means to the right of the wall. Both E and E minus V naught are positive because here E is greater than V naught. So if E minus V naught should be positive. So when both are positive, it is easier to interpret using exponential function. So the solution should look like this. Okay, the solution of the Schrodinger equation are psi 1. This is in the region. The one here indicates the region before or to the left of the wall, potential wall. Okay. So you have A1. This is the solution we had discussed previously. I square root 2 ME per H bar. There is no V here because for x less than 0, V equal to 0. Look back at the diagram. Okay, so you have this, and it's actually equal to this. Okay, you actually we replace the terms there with K1. The definition for K1 is here, and definition for K2 is here. You can say that K can be the wave number in region 1, that means to the left of the step potential, and K2, you have here the difference in energy and potential. It is K2 to the right of the potential well wall. Okay, the wall of the potential well. Okay, so basically we replace this with K1. Okay, for set to ME per H bar. So it looks simpler rather than all those things. The same thing for the psi 2. This is in the region 2 to the right of the potential wall. Okay, you have this for x greater or equal to 0, and it reduces to this in terms of k. But now we have K2. That means in region 2. The subscript 2 means region 2 to the right of the wall, and subscript 1 indicates to the left of the potential wall. A1, A2, B1 and B2 are constant which need to be determined from the boundary condition. So we have constant A1, A1, B1, A2, B2. Okay, so we need to determine A1, A2, B1 and B2. This is more or less the, what you call it, the constant representation in this figure. The constant A1 basically in region 1. This, so to the left of the potential wall, this is region 1. To the right, it is region 2. I mean from here up to here. So that you can see the constant A1 and B1 is in this region on the left of the potential wall, and A2, B2 to the right of the potential wall. And remember that the solution for constant A1 is a wave moving to the right. B2 is for a wave moving to the left. The same thing for in region 2, we have A2 is for a wave moving to the right, and B2 wave moving to the left. Okay, so this is the representation of the constant, and E is higher than V naught. This is V naught. This is V equal to 0. So V naught is a Stern value of V, while V0 is here. Okay, so B2 term represent a particle originating at x equal to positive infinity. If you look in this diagram, B2, it originates from positive infinity to the right there. B2 move a wave moving to the left from the right. But in our case, actually the wave or the particle is from the left to the right, not from the right to the left. Therefore, there is no particle originating from positive infinity. There is no way to produce such a particle trajectory from a particle initially moving to the right on the left-hand side of the step. So, set B2 to 0. So, since actually our experiment is a particle moving to the right, so there is no way that B should be there. So, B should be 0. There is no particle coming from positive infinity. Okay. Then the wave function is simplified to the first one, psi 1, does not change, but psi 2 now only depend on A2 because B2 is already set to 0. Okay. So for psi 2, we have only one term. If you look back in the diagram here, you have a wave coming from the left. Some might pass, but some might be possible to be reflected at this step potential, but there is no way a particle from infinity. Because of that, B2 is set to 0. That's why the first wave function, psi 1, contains both A1 and B1, but the second wave function, psi 2, contains only one term containing A2 only. Okay? So this is it. So now we look at the boundary condition. The first boundary condition at x equal to 0, that means at the position of the potential wall. Okay. So x equal to 0, x equal to 0. When x equal to 0, all this become 1. All the exponent become 1. So psi 1 when x equal to 0 is A1 plus B1. Equal to psi 2 when x equal to 0 equal to A2. Okay. So this is the first boundary condition. That means the wave function on both sides of the boundary should be continuous. The second boundary condition is that the differentiation or the differential between psi 2 1 and psi 2 on both sides of the boundary should be equal. So we have d psi 1 per dx equal to d psi 2 per dx. So when you differentiate, basically with respect to x, the coefficient of x should be multiplied with the real number, the number a1 here. That means now we have I k1 a1, then minus, because of the negative sign here, you differentiate minus I k1 b1. This must be equal for the second wave function I k2 a2. Now we have two equations. It is 1, this is 2. Okay, can we solve these two equations? Apparently cannot. Why? Because we have three unknowns, but we have only two equations. Remember that in mathematics, in order to solve unknowns, you must have the number of equations must be the same as the number of unknowns. For example, if you have two unknowns, you must have two equations. If you have three unknowns, like this, you should have three equations. If you have 10 unknowns, then you need to have 10 equations. Okay, in order to solve the unknowns. Okay, but here we have three unknowns, but only two equations. So cannot be solved. Cannot solve the constant as we have three unknowns and only two equations. But what we can do, we can express the unknowns in terms of the third one. Okay. So let us, in this example, keeping A2 as our only unknown. So that means A1 is now defined in terms of A2. B1 is now defined in terms of A2. That means by solving the two equations, so that we have only one unknown in the equation, in the final solution. So A1 should be in terms of A2 and B1 should be in terms of A2 like this. Okay. So we can put back the wave function now becomes A1 we replace with A2 per 2 and so on and so forth, while uh, B1 is represented by this, okay? The constant A1 and B1 for region 1. That means to the left of the potential wall. Okay, we have this solution. What does it mean physically? That means what does this two wave function with respect to x means? So we have to define the probabilities because we know that psi itself does not mean anything, but psi squared is the probability density. Remember we had discussed a few segments ago, okay? Psi squared or psi conjugate multiplied by psi itself will give you the probability density. So we can define the probabilities that the particle will be reflected at the step. We represent it by R, reflected, that's in reflection, or in the title of this segment is called scattering, scattered back or reflected, and that it will be transmitted across the step is represented by capital T, that means transmitted, okay, R and T. So what we can do is define probabilities because psi itself, the wave function itself does not really mean physically anything, does not have really physical meaning, but the psi squared will give you the probability. In classical electromagnetism, when we studied electromagnetic wave, the reflected wave is equal to reflected amplitude squared divided by the incident amplitude squared. So we have the amount of electromagnetic wave being reflected back or being scattered back, while transmitted electromagnetic wave is equal to transmitted amplitude squared divided by the incident amplitude squared. There should be an R here. Okay, so you can see that in classical electromagnetism, it depends on amplitude. Okay, and as a whole, R plus T should be equal to 1. That means the total of reflected amplitude of electromagnetic wave plus the transmitted amplitude is some sort of must be equal to 1. That means as a whole, reflection and transmission equal to 1. Since the particle must be either transmitted or reflected. That means it should be equal to 1. The same thing with a classical electromagnetic wave. When you add the amount being transmitted and being reflected, it should be equal to 1. So using that analogy, we now define the wave function of the particle using more or less the same method. B1 here is the reflected constant, isn't it? B1 in the region 1 is going from right to left, while A1 is the incident particle constant. A1 is from left to the right. It is all in region 1, that means before the step potential. So we can define reflected particle as B1 conjugate multiplied by B1 divided by A1 conjugate multiplied by A1. So here we can determine the reflection of the particle at the step potential, and it is equal to K1 minus K2 squared divided by K1 plus K2 squared, and it is defined, K is defined as in the a few slides ago. Okay, yeah, K1 equal to square root 2 ME per H bar. Here basically the particle have M and also have E, so it should not be 0 at all. So we come back to here, that means this solution are non-zero solution. That means it has certain values. R here is defined as the probability of being reflected. And since we have this relationship, R plus T must be 1, So we can determine T, the probability of the particle to be transmitted, equal to 1 minus R. So 1 minus the same thing here, up here, we bring it down here. So if the top one is non-zero, 1 minus something non-zero should be non-zero too. So what we have basically, in quantum mechanics, both R and T are non-zeros. That means it has certain values. Even though it might be, one might be bigger, the other might be smaller, but it is not zeros. In other words, this is what we call as remarkable result. There is a non-zero probability that the particle will not be transmitted across the step, but will actually reflect it back. Classically, if looking back at the diagram here, okay, here, classically, at high potential here, at high E, E higher than V naught here, a particle should pass right through, moving from left to the right. The particle should be transmitted through. There is no reflected particle, okay? Except that the momentum changes, okay? Remember, the momentum changes because of the difference between E and V naught. But there will be no particle being reflected back. That is in classical mechanics. But in quantum mechanics, the probability, we are talking about probability of particle to be transmitted is there, non-zero. And the probability of being reflected back also non-zero. That means some of the particle can be observed to pass through, but some particle will be observed to be reflected back from the step potential. That's why we call it remarkable result, because it is not similar as in classical mechanics. In classical mechanics, all particles will be transmitted through. But in quantum mechanics, some of the particle might be reflected back, even though the energy of the particle E is greater than V naught. That means greater than the potential wall here. So this is the remarkable results, which sometimes we against our intuition. What we have in mind, if a particle being shot through, that means the energy is above the potential V naught, all the particles should go through and no particle should be reflected back. But from our mathematical process, we had done, we see that both are non-zero, the R and T are non-zero. That means some of the particle will actually be reflected backwards. Okay. The question: why such reflection is not observed in classical system? In any real physical system, the step function potential will have a non-zero width in the x direction. Of course, when we draw the diagram of the step potential, we expect that V naught will continue to infinity. So as long as this width is much larger than de Broglie wavelength of the particle, the system will lie in the classical regime. So if the width of this, that means the width of the V naught is much larger than the de Broglie wavelength of the particle, the system is still valid if you use classical mechanics. That means the particle should go on and on lah, without any being reflected back. That's why we always say that the classical system is the limit of the quantum mechanical system. Quantum mechanical system, basically, it covers everything. That means whether it is in the limitation of certain values or whether it is whatever situation, the quantum mechanical system represents them all. Such as, for example, just now we can see that the wave function psi is actually for both representing the wave going to the right and to the left. Okay, so only in certain condition that quantum mechanical system is equal to the classical system. And an example: how narrow will the step function potential need to be in order to observe quantum effect? So what's the the width of the length of the V naught in order for us to observe quantum effect. So if we consider an electron accelerated through a 100-volt potential difference, the energy of the electron is E equal to this is the unit charge multiplied by the potential difference. You have 1.6 times 10 to the negative 17 joule. De Broglie wavelength, basically lambda equal to h over p. It is about 1.2 multiplied by 10 to the power negative 10 meter. So here is the size order of the size of the de Broglie wavelength, 10 to the negative 10. So the potential needs to rise from 0 to V naught in a length less than about an atomic radius, because atomic radius is about this size, okay, or even sometimes up to 10 to the negative 12. So generally, quantum effect in state oscillation can only be seen at the atomic or nuclear level. So in order to have to see the effect of the quantum mechanics in this case, the step function potential should be at the atomic or nuclear level. That means if nuclear, it is Fermi, 10 to the negative 15. But at least 10 to the power 10 meter for an electron. Okay. In conclusion, classically, there should be no scattering or no reflection at the step potential if E, that means the energy of the particle, is greater than V naught. Quantum mechanically, however, the values of both R and T, that means the probability of being reflected, T is the probability of being transmitted, are non-zeros. So there are probabilities that some particles are reflected or scattered and some are transmitted. So these are the differences between classical mechanics and quantum mechanics. So quantum mechanics predicts that even if E is greater than V naught, we have some probabilities that some of the particle will be reflected back. Thank you very much for your attention.